este seminario, donde vamos a tener el privilegio de escuchar a un joven investigador que nos visita desde Palermo, en Italia, que es el doctor Claudio Inguaggiato. Bienvenido,
Gracias.
Claudio.
Muchas gracias.
Bueno, Claudio obtuvo muy recientemente su doctorado, en febrero de 2016. Trabaja como investigador temporal en la Universidad de Palermo y es colaborador científico del Instituto Nacional de Geofísica y Vulcanología de Palermo. Se especializa en geoquímica de tierras raras, como circonio hafnio, en sistemas hidrotermales. Y también ha trabajado en caracterización geoquímica de gases. Creo que todos estos temas son de gran interés para nosotros. Resultado de sus líneas de investigación son 8 artículos publicados, 2 enviados y 1 en preparación. Sus trabajos han sido presentados ante foros nacionales e internacionales con mucho éxito. Hoy tendremos la oportunidad de escuchar parte de su trabajo relacionado con los 2 temas anteriores, que son estos. Entonces demos la bienvenida a Claudio y adelante.
Muchas gracias por todo. Yo voy a hablar en inglés.
Ok.
Idioma.
Ok.
Firstly, please. Si sente? Escucha. Firstly, I would like to thank you, the University, the UNAM, to invite me here today, and for all the people for being here. And I am Claudio Inguaggiato, and this is part of my presentation of my PhD. And I am going to present 2 different topics. And the first one is the geochemistry of rare earth elements, zirconium and hafnium in extreme water environments, particularly hyperacid, hypersaline, and lake waters in hydrothermal systems. And I will focus the attention on this topic. And the second one is the geochemical characterization of gases along the Dead Sea Rift, that is an hydrothermal system, where we found evidences of mantle carbon dioxide and mantle helium degassing. Okay. The first question that we have to do is what are the processes controlling rare earth element zirconium and hafnium in natural waters? About the rare earth element that are composed by lanthanides and yttrium, we have to know that are a resource economically important due to the continuous exploitation of this element for electronic devices. Previously, zirconium, hafnium, and the rare earth element were considered immobile elements in waters, and most of the studies were carried out on the rocks. Recently, with the improvement of the techniques to analyze the trace element, in the last 20 years started the work about the rare earth element and zirconium and hafnium in natural waters. The rare earth element fall in the block F of the periodic table, and all the rare earth elements are characterized by oxidation state 3+, with the exception of cerium and europium that have also respectively the oxidation state 4+ and 2+. The ionic radius of rare earth element decrease from lanthanium to lutetium, increasing the atomic number of these elements. The majority of the researches about the rare earth element were carried out in the seawater. And this is the starting point of the study of the rare earth element in natural waters. In this plot, we can observe the typical distribution of the rare earth element normalized to the post-Archean Australian shale. In particular, this plot is relative to the Mediterranean seawater, but is very similar to the oceans. And we can observe that the distribution of rare earth element increase from lanthanium to lutetium. The study of processes involving the rare earth element in the thermal system is very limited. We have some studies in the Yellowstone Park by Lewis, Gammons et al., and a review about the rare earth element in the hydrothermal system by Wood. But until now, there is a paucity of knowledge of this element in the natural waters. The total amount of rare earth element in geothermal water changes over 4 orders of magnitude. higher than the seawater composition. About the zirconium and hafnium in waters, the knowledge is very limited, and all the works that were carried out are in marine environments. We know about the chemistry of these elements in water that zirconium and hafnium occur in waters are stable as hydroxyl complexes. In particular, we have the zirconium that is neutral charged and the hafnium that is negatively charged. Recently, zirconium and hafnium have been proposed as a tool for tracing the water masses in the ocean, where Frank and Firdaus found a preferential removal of hafnium with respect to zirconium along the pathway of water masses. So until today, we have a lack of knowledge about the groundwater geochemistry of rare earth elements and zirconium and hafnium. I would like to introduce also the fraction action of yttrium holmium and zirconium hafnium elements. Yttrium holmium and zirconium hafnium are elements characterized by similar ionic radius and the same charge. Yttrium holmium have oxidation state 3+, and zirconium hafnium have oxidation state 4+. It's interesting to study these elements because during the processes involving the pure silicate melt as the crystallization of the magma, yttrium holmium and zirconium hafnium pairs are mainly ruled by the charge and the radius. In fact, we didn't find fraction action in the magmatic rocks. These processes were called by Bau in 1996 Karak processes, charge and radius controlled. On the contrary, Bau highlights that these elements in the aqueous solution and in solid phase precipitated from this water are characterized by different ratios and show a fraction action that is not negligible. In this plot from Bau in 1996, we can observe that the magmatic rocks fall in the Karak field where there is the chondrite ratios for yttrium holmium and zirconium hafnium. On the contrary, in seawater and the hydrogenetic iron manganese crust investigated in the bottom of the ocean, we can observe that there is a fraction action of these elements. And this is not due to the charge and the radius. So the aim of this work is to investigate the geochemistry of zirconium, hafnium, and the rare earth element in the wide range of chemical physical conditions and water composition. In order to do this work, we have chosen 3 different environments that have important different features. In particular, the first one is Nevado de Ruiz volcano hydrothermal system that was chosen for the wide range of pH from 1 to 8. The second one is the Dead Sea Fault area in Israel that was chosen for the wide range of total dissolved salts from 0.3 to 200 grams per liter, and the wide range of redox condition from negative to positive values. The third case of study is in Italy, and is Pantelleria volcano hydrothermal system, where we investigate the focused attention on the Specchio di Venere lake that have an alkaline pH of 9. The temperature, the pH, the electrical conductivity, and the age of waters was measured on the field with a multi-parameters instrument, the Orion Plus. And the water were filtered through 0.45 micrometer per side filter, and then acidified with the ultra-pure solution of nitric acid. The bicarbonate concentration was measured directly on the field by treatation with the chlorhydric acid. And the major species were analyzed by Dionex ion chromatograph, and the trace elements, including also the rare earth element zirconium and hafnium, were analyzed directly by ICP-MS with an external calibration. In some cases where the concentration was over rare earth element and zirconium hafnium was very low, and the salinity was high, as in Pantelleria and Dead Sea Fault area, we have pre-concentrated the water following the method of Raso et al. In 2030, and then we analyzed the elements with the same instrument, the ICP-MS. The solids were investigated by scanning electronic microscopy in order to have an idea about the secondary minerals precipitating in the investigated waters. So the first case of study is the geochemistry of rare earth elements, zirconium and hafnium, in the wide range of pH and water composition. And this is the case of the Nevado de Ruiz volcano hydrothermal system that probably we know better than me. Nevado de Ruiz is one of the active volcanoes belonging to the Great Chain of the Andes. In this area, the Nazca Plate descends below the South American Plate, generating the Great Chain of the Andes. In this map on the left, we can observe the sampling point that were close to the Nevado de Ruiz volcano. And the waters, as I said before, are mainly characterized by a pH from 1 to 8 and temperature from 7 and 80. The EH values are always positive with the exception of one sample that is slightly negative. And the electrical conductivity was very low from 1 and 2, with the exception of only one sample that have 33 millisiemens. About the local rocks, there is the study of Borrero et al. In 2009, where he studied the rocks, and he found that the rocks are characterized by calcaline rocks ranging from andesitic to dacitic composition. And in the graph, we can observe the analysis of the average values of the analysis of Borrero et al. About the rare earth element normalized to the chondrite, and we found the typical distribution pattern of rare earth element decreasing from lanthanum to lutetium. Moreover, yttrium, holmium, and zirconium hafnium molar ratios have a negligible variation in the local rocks investigated by Borrero et al. And the same way have ratios that are comparable to the chondrite, so there is no fraction action during the crystallization of the rocks. We have classified the water into different groups as function of the pH values. We have the group 1 that are near neutral waters with pH higher than 6, and the group 2 that are acidic water with pH lower than 3.6. In addition, we have subdivided this water in 4 groups as function of the major anion contents that are very important for the rare earth element because are the ligands that are able to compress the rare earth element in waters. We found that group 1 A is characterized by higher bicarbonate concentration, while group 1B is only one sample, Botero Londonio, that is chlorine dominated. But now we focus the attention on the acidic waters, the group 2, that is divided in the group 2A and the group 2B as function of the different sulfate chlorine ratios. The isosol diagram was used to express the elements relations for near congruent dissolution of the rocks. This plot that was proposed by Varekamp in 2001 showed the element concentration in the primary rocks and element concentrations in water. This line, the straight line, are the isosol line, so all the symbols that fall along this line represent the congruent dissolution of the rocks. We focus the attention in the group 2 waters, that is group 2A and group 2B. We can observe that the circle symbols that are relative to the water of group 2B close along the isosol line, suggesting that the evidence that we have with major elements is to be near congruent dissolution. So the major elements are mainly controlled in the water of group 2A by water-rock interaction without fraction action. On the contrary, the water of group 2A that is indicated in the graph with the square deviate with respect to the isosol line for the aluminum, for the iron, for the calcium and for the sodium. And this is are elements that normally in this sulfate water precipitate as alunite and jarosite minerals. So we can identify from this graph that could occur fractionation processes of major elements by precipitation of these minerals only in group 2A. About the group 1A and B, we can observe that for iron and aluminum, there is a strong deviation with respect to the isosol line. This means that iron and aluminum are precipitated in waters and as secondary minerals. And this could be due to the different pH of the group 1 that is close to 6. So are stable the secondary minerals as iron oxidroxide and aluminum oxidroxide. We have investigated the solid phases that remained on the filters during the filtration in the field. We can observe that in this figure is representative of the group 1, and the ADS analysis suggests that there is iron and aluminum and also silicium. So we propose that there are iron aluminum oxidroxide on the surface of amorphous silica. In group 2B, we didn't find iron oxidroxide, we didn't find nothing of as solid phases precipitated, while on the contrary, in the group 2A, we found iron, sulfur, potassium, and also aluminum in the solid phase onto the filters. These are elements forming jarosite and alunite minerals. We have also carried out simulation with the Frequency software in order to have an idea about the saturation indexes of these minerals in waters, and these solid phases are in according with the result of the Frequency. About the rare earth element, we found in this environment a wide range of concentrations from 0.30 nanomole per liter to 6,000 of nanomole per liter. And the total amounts of rare earth element seem to be function of pH values. In fact, we can observe that we have in the group 2 water, that are the acidic water, higher concentration of rare earth element with respect to the group 1 waters. In order to investigate the water-rock interaction in these environments, we have normalized the rare earth element analyzed in water to the average local rock before presented. We can observe that the group 1A is characterized by patterns increasing along the rare earth element series, positive europium anomaly, and negative europium anomaly, cerium anomalies. About the group 1B, we have a flat pattern that slightly decreases along the rare earth elements. But focusing the attention in the acidic waters, we have two different patterns. We have that the group 2A is characterized by a strong depletion of light rare earth element with respect to the middle and heavy rare earth element. On the contrary, the water of group 2B, that are always acidic water, show a flat pattern. In this plot, we can observe the yttrium versus zirconium hafnium changes, and we found a different behavior of this element in group 1 and group 2 waters. We have that we have a wide range of values. Yttrium change from 48 to 130, while and are chondritic and superchondritic values. The same for the zirconium hafnium in group 1. On the contrary, we found that zirconium hafnium have a wide range between 5 to 105 subchondritic and superchondritic values. This is the first time that zirconium hafnium are analyzed in acidic water, so we cannot compare this data with the other hydrothermal system. But it's the first time also that we found that the scientific community found subchondritic zirconium-hafnium values in waters. Now we discuss a little bit about the data just presented. About the pattern of rare earth element that we found, we can justify the pattern considering the precipitation of secondary minerals in waters. In group 1A, we found this pattern increasing along the rare earth element series. That this is in according with the coefficient of a partition, the KD, between the rare earth element in iron and manganese oxidroxide normalized to the waters. We can observe that the patterns found in waters is the inverse, the contrary, with respect to that found in during the precipitation of these minerals. This is in according with the secondary phases that we found by scanning electronic microscopy and with the phase suggested by the frequency simulation. But now we focus the attention on the group 2A and 2B that are acidic water but have a different pattern. The group 2B is easy to justify. This is due to the near congruent dissolution of the rocks. So we found when normalized to the rock, we have a flat pattern. And this is fit with the information that we have by the major elements that in group 2B fall along the isosol line of the near congruent dissolution. On the contrary, the group 2A is the only one where we found the precipitation of secondary minerals as alunite and jarosite. So we can explain this different fraction action due to the precipitation of these sulfate minerals. After this study that is already published recently, there was an article that was just published that present the distribution pattern of rare earth element in the alunite and jarosite minerals. And if we compare, we have a pattern that is inverse with respect to this. About the cerium anomaly, we can observe that there is a variation that is due to the pH. Why there is this variation? In the acidic water, where the iron aluminum oxidroxide don't precipitate, we have values that are close to 1, so the cerium anomaly is negligible. But in the waters characterized by higher pH, where we found the precipitation of autogenic minerals as iron and aluminum oxidroxide, we have a different anomaly of cerium, so there is a strong negative cerium anomalies. And this is in according with the study experiments carried out in laboratory by Seto et al. In 2008 and Bauer-Koschiski in 2009 that found that the cerium that have a different oxidation state with respect to the neighboring elements lanthanum and praseodymium are characterized by a strong scavenging onto the surface of these minerals. Now we focus the attention about yttrium holmium and zirconium hafnium, and we add another information with respect to before. So in the group 1, where we found these superchondritic values for yttrium holmium and zirconium hafnium, is the only group of water where occur the precipitation of iron and aluminum oxidroxide occur. Holmium, and we can justify this decoupling of these elements by the different affinity of hafnium and holmium with respect to the iron and aluminum oxidroxide. So hafnium and holmium are mainly scavenged by the iron aluminum oxidroxide with respect to yttrium and zirconium. This is the reason because we found these superchondritic values. On the contrary, in group 2, acidic waters, we have not the precipitation of iron and aluminum oxidroxide. Holmium is not scavenged with respect to yttrium, and then we have values that are the same of the chondritic ratios, so the same of the rock that we can observe, indicated in the graph with the circle symbol. But a different behavior of zirconium hafnium occur. So Now we concentrate the attention only about zirconium and hafnium in the acidic waters. Before we subdivided by the anion classification the water in group 2A and group 2B, and this classification was done with respect to the different chlorine sulfate ratios. Until now, we only know that the speciation of zirconium hafnium in natural waters, pH between 6 and 8, is mainly controlled by oxydyl groups. But in this case, we don't know if zirconium and hafnium are complexed with another ligands, anions. Because normally, we have not this higher amount of chlorine and sulfate in waters. In fact, we can observe that there is a different fraction action that could be function, or is better to say, subdivided into group with as function of the chlorine sulfate ratios. So we propose that the formation of chlorine and sulfate complexes could be responsible of these different fraction action and the subchondritic zirconium-hafnium ratios found in these environments. So the conclusion of this first part are that the alunite and jarosite remove the light rare earth element with respect to mid rare earth element and heavy rare earth element. The negative cherry anomaly is due to the precipitation of iron and aluminum oxide, and the precipitation of these minerals is function of the pH of the water. The precipitation of these minerals, iron and aluminum oxide, is able also to decouple the yttrium-holmium and zirconium-hafnium pairs with enhanced scavenging of hafnium and holmium with respect to zirconium and yttrium. The last point is that in strong acidic water, the zirconium-hafnium molar ratios is function of chlorine sulfate molar ratios, and we propose the formation of chlorine and sulfate complexes that are able to lead the values up to the superchondritic zirconium-hafnium ratios. Now I am going to introduce the second part of the study that concerns the geochemistry of rare earth element zirconium and hafnium in the wide range of pH and water composition that we found along the Dead Sea Fault system in Israel. In this area, lateral displacement of 100 kilometers occur between the Arabian plate and the African plate. The main chemical physical parameters that we have to consider is the strong variation of pH and the strong variation of total dissolved salts. In these graphs, we present the major chemical composition of the waters. We can observe that in the anion plot, we have the waters that fall along the line joining the chlorine and bicarbonate corners. While there is a group of water that deviate with respect to this alignment towards the sulfate corner. About the cation major composition, we can observe that most of the samples are close to the sodium-potassium corner, and the main component is the sodium in this case. And we have a group of waters that move towards the calcium corner. So this group of water is the same before presented, and this could be due to the gypsum dissolution that was already recognized in this area. On the contrary, when we found the waters that are chlorine dominated, this is due to the ancient brine that there are in these environments, and or the strong dissolution of halite. We have classified the waters into different groups as function of the pH values and the saturation indexes of minerals. That number is 100, like 1 that is. The group 1, all the waters are undersaturated in gypsum and halite and are close to the saturation with respect to the carbonate minerals. But a strong difference was found between the iron oxide and pyrite. We can observe that the group 1 water are characterized by iron oxidroxide that are saturated or oversaturated, and always undersaturated with respect to pyrite. In this case, the EH values are always positive, between 100 and 260. On the contrary, the group 2 water that are characterized by negative EH values are always undersaturated with respect to the iron oxidroxide, but are oversaturated with respect to pyrite. These two same images are representative of the group 1 and group 2 waters. And we found in group 1 waters possible iron manganese oxidroxide and carbonate minerals, while in group 2 we found that the ADS analysis is mainly composed by sulfur and iron, and this is possible pyrite. About the rare earth element, we have normalized the rare earth element dissolved in water to the post-Archean Australian shale, because in this case it's not so simple as in Nevado del Ruiz, because we have not an average local rocks, because we have a variety of rocks in this environment as carbonate minerals, gypsum, and light. But the main difference that we found is that in group 1 waters, most of the waters are characterized by a middle rare earth element enrichment and a negative cerium anomaly. On the contrary, the group 2 is characterized by a flat pattern compared to the group 1 waters, but there is an unusual europium anomaly, positive, very strong positive europium anomaly. About the yttrium, holmium, and zirconium hafnium, we have a wide range of values, but we found that only in group 1 waters with positive EH values, we have the simultaneous fraction action of yttrium, holmium, and zirconium hafnium towards superchondritic values. On the contrary, in group 2, yttrium, holmium, and zirconium hafnium have a different behavior, and we have that yttrium, holmium fractionate with respect to superchondritic values, while zirconium hafnium are quite constant, close to the chondritic ratios. Now we discuss a little bit the patterns of rare earth element and the difference found. The water of group 1 are the same that are characterized by this enrichment in sulfate that was justified by the gypsum dissolution. So the question is, the gypsum dissolution is able to enrich the middle rare earth element in the waters? The answer is yes, because data from Tulkeridis in 1998 about the distribution of rare earth element of the gypsum normalized to the post-Archean shale show this pattern that is enriched in middle rare earth elements. On the contrary, about the group 2, we focus our attention on the unusual europium anomaly, positive europium anomaly. I say unusual because normally it's usual to find this anomaly in where there are waters that interact with magmatic rock, with calcium plagioclase, that is enriched in europium. But it's not the case. In this graph, we compare the europium and the cerium anomalies. We can observe that the group 1 waters that have positive EH values, where the iron oxidroxide precipitate, we have the negative cerium anomalies, as found in the previous system. On the contrary, we have that the water of group 2, where EH are negative, are characterized by a negligible cerium anomaly, and the iron oxidroxide cannot precipitate in this system with this EH, but we have a strong fraction action of europium with respect to the neighboring elements with values of anomaly that arrive up to 7. We can justify this different behavior of europium due to the different oxidation state of europium with respect to the other elements, because europium have two different oxidation states, europium 2+ and europium 3+. But europium 2+ is more stable in the aqueous solution and have not affinity with respect to the solid phase, because europium is characterized, the 2+, by a radius that is higher with respect to the europium 3+ and the neighboring elements. So he preferred to remain in a water solution with respect to samarium and gadolinium. This is this idea is corroborated also by frequency analysis that show that the europium in water is dominated by the europium 2+. Now we focus the attention about the zirconium hafnium versus EH values. The plot on the left shows that zirconium and hafnium ratios increase as EH values increase. But zirconium and hafnium are not redox sensitive elements. So this different fraction action is due to the precipitation of minerals that are controlled by the redox condition of the system. In fact, we can observe that zirconium-hafnium molar ratios are higher, significantly higher with respect to the chondritic ratios, only in the case when the saturation index of iron oxidroxides increase. So, precipitate these minerals. How to explain the fraction action of these elements as a function of the precipitation of iron oxidroxides? Until now, we know that zirconium-hafnium speciation in near neutral waters is included between 6 and 8, and is characterized by zirconium that is neutral charged and hafnium that is negatively charged. In group 1, when pH is less than 8, and this case, iron oxide surface are positively charged. On the contrary, the group 2, where we found only pyrite as a stable minerals, and the pH of the water is close to 6, the surface of the pyrite is neutral charged. So we applied a model that was already used for other trace elements by Konshiske-Dane in 2003. So the electrostatic process that can scavenge the negatively charged hafnium onto the surface of the positive iron oxidroxides. We propose this model to fractionate these two couple of elements. In conclusion, we have that the middle-layer element enrichments in water are due to the dissolution of gypsum, that cerium and europium anomalies change as function of EH values, that zirconium-hafnium molar ratios increase as EH values increase, and the positively charged surface of iron oxidroxide could remove preferentially hafnium that is negatively charged with respect to zirconium that is neutral charged. This is the third part about the rare earth element zirconium and hafnium, and I am going to present the zirconium, hafnium, and the rare earth element signatures, discriminating the effect of atmospheric fallout from the hydrothermal input in volcanic lake water. Some background information about Pantelleria Island, that is located in Italy in the Strait of Sicily. Pantelleria Island is an active volcano and is 70 kilometers far from the Tunisian coast. So inevitably, all the fallout, atmospheric fallout delivered by the Sahara Desert involve the Pantelleria Island. In Pantelleria, with the circle point, we are indicated the sampling point in Pantelleria Island, and here there is the Specchio di Venere Lake. We collected different kind of waters, mainly hydrothermal waters, and in addition we have collected two different water sample in the Specchio di Venere Lake. One is a shallow sample, and the other one is deep water, less 13 meters. About the major elements that are already investigated by other researchers, we can observe that in the anion plot, the water sample fall along the line joining the chlorine and alkalinity corners. And about the cations, we have that all the waters fall close to the sodium-potassium corner and close to the seawater composition that is indicated with the star in both the plots. Previous studies have already explained this pattern from chlorine to alkalinity corners by mixing processes between seawater, meteoric water, and the enrichment in carbon dioxide is justified by the interaction between the carbon dioxide of magmatic origin and the waters. But the interesting point in these two plots is to observe the lake water composition that is indicated with the red symbol. We have only one point because the chemical composition of the lake water, about the shallow and the deep, will remain the same. There are not fraction action of major elements. So there is a quite constant major chemical composition in the top and the bottom of the lake. We have collected sample from Specchio di Venere Lake, and another sample that is important is Polla 3 thermal waters that feed the lake waters. In particular, we found as a suspended particular matter amorphous silica, mainly amorphous silica in the Polla 3 thermal spring, while this picture, these same images, is from the shallow part of the water, where we investigated a suspended particular matter that seem to be characterized mainly by phyllosilicates and possible iron oxidroxide. In this plot, I present the rare earth element dissolved in water, normalized to the post-Archean Australian shale. We found total amounts of rare earth element that range between 2.7 up to 12 nanomole per liter, and we found the higher concentration of rare earth element in the lake waters. I plot as reference the seawater composition that is the lowest in concentration with respect to the investigated water in Pantelleria. But it's interesting to observe that all the waters collected in Pantelleria have this pattern that increase from lanthanum to lutetium. The only exception was found in the lake water, that these are two different samples, the top and the bottom of the lake, that are characterized by the same distribution pattern. So the rare earth elements don't fractionate between the top and the bottom of the lake. But why we found a mid-rare earth element enrichment in lake waters? About yttrium, holmium, and zirconium hafnium, we found that there are values that are in a wide range, with the exception of zirconium hafnium and yttrium holmium in the water lake, that have similar values in the top and the bottom of the lake. We found also in the lake the higher concentration of yttrium, of holmium, of zirconium, of hafnium, and the lowest yttrium, holmium, zirconium, hafnium ratios. About the cherry anomaly, because presented, we can observe that the cherry anomalies change as function of the AH values. And this is according to the other system before presented, and this is always due to the precipitation of iron oxidroxides. But a different behavior of cerium was found in the water lake, the top and the bottom of the lake. We propose that this enrichment of cerium is due to the interaction of the water with the dust saran particulate that come from the desert, that is enriched in cerium. So the interaction with the dust particles could change the cerium anomaly. So now the question is, what is the main process controlling the geochemistry of rare earth element in Specchio di Venere Lake water? In order to better understand what are the processes that involve the rare earth element in these environments, we have considered the study of Goldschmidt et al. In 2014 and another study that concern the rare earth element distribution and the zirconium hafnium in the desert varnish and the dust that there is in the Sahara Desert. And that these solid phases are mainly composed by iron oxidroxide and clay minerals that are the same that we found in the shallow waters phase. And we can observe here the rare earth element of the desert varnish normalized to the post-Archeano-Australian shale. We observe this positive cerium anomaly in the solid phases and also this bulge effect, so this middle rare earth element enrichment with respect to the light and the heavy rare earth elements. In addition, Graves in 1994 carried out an experiment in laboratory where about the mobilization of the rare earth element from the Sahara Desert to the Mediterranean seawater. And he found that are higher mobilized the middle rare earth element in waters with respect to the light and heavy. So if we observe the pattern that we found in the water lake, that is the blue symbol and the red symbol, we can observe this middle rare earth element enrichment with respect to the Polla tree, that is the thermal spring that feed the lake. So there is something that other rare earth element, and all this information suggests that the middle rare earth element enrichment is due to the interaction with the Saharan Desert aeolian input. In fact, we can observe that the heavy metals are the same, have the same distribution of that found in the Polla tree thermal spring that feed the lake. About yttrium and zirconium hafnium ratio, we can simply observe that all the yttrium and zirconium hafnium values of the other waters collected in Pantelleria Island have a wide range of values. On the contrary, the water of the lake have a signature that is the same found in the desert varnish. So this information is important because suggests that also zirconium and hafnium come from the aeolian dust. In conclusion, for this third part, we can say that the rare earth element zirconium and hafnium contents are higher in the water lake compared to the thermal waters, that the rare earth element patterns in waters increase from lanthanum to lutetium, whereas lake water is enriched in mid rare earth element as the desert varnish. Cerium anomaly is function of EH values as found in the other environments investigated, but the cerium enrichment in the lake is due to the atmospheric fallout that come from the desert, Sahara Desert. At the end, we found that the rare earth element coupled with the yttrium and zirconium hafnium ratios showed to be a geochemical tracers that are able to identify the contribution of the Saharan particulate from the North Africa in the Specchio di Venere Lake, discriminating the hydrothermal input of the Polla tree. So the overall conclusion for this the part relative to the rare earth element zirconium hafnium are that the total amounts of rare earth element in waters is inversely correlated to the pH. Cerium and europium anomalies are function of pH and pH. The light rare earth element in water appear to be removed from alunite and jarosite minerals in the acidic sulfate waters of Nevado del Ruiz system. The dissolution of gypsum along the Dead Sea Fault in Israel release preferentially middle rare earth element in waters. The subchondritic zirconium hafnium ratios were found for the first time in the acidic waters and showed variation that are related to the chlorine sulfate ratios. About zirconium hafnium ratios, we can say also that changes were found as function of EH values, but this is not directly correlated to the oxidation state of the elements, but is due to the different stability of iron-bearing minerals. In neutral waters, we found in all the studies that hafnium is preferentially removed with respect to zirconium by iron oxide. At the end, we propose that the zirconium, hafnium, and the rare earth element are potential tracer and can be used in other water lake to discriminate the hydrothermal input with respect to the fallout, the atmospheric fallout. Now we finish the part that is relative to the rare earth element zirconium and hafnium, and I would like to present a condensed version of this last study, concern the geochemical characterization of gases along the Dead Sea Rift hydrothermal system and evidences of mantle carbon dioxide degassing. The investigated area is the same before presented. We are along the Dead Sea Fault area. This is the Red Sea, and this is the border with Syria and Lebanon. And the aim of this work is to find the source of carbon dioxide and helium along the Dead Sea Fault, and to find a relationship with the main tectonic framework of the area. In order to do this, we have collected sample of dissolved gases. Helium and carbon isotopes were investigated in the cold and the thermal waters that are located along the Dead Sea Fault. These are the sampling points that are indicated with the red symbols in the map. We can observe that we investigated almost all the Dead Sea Fault. And this triangular plot shows the chemical composition of major gases, oxygen, nitrogen, and carbon dioxide. And we can observe that there exist mixing processes between a carbon dioxide-rich end member and a shallow air-dominated system. In particular, the water that are characterized by carbon dioxide-rich end member are located in the northern part, and are these four samples. The binary plot shows the carbon dioxide and helium concentration in waters. We can observe that carbon dioxide and helium increase simultaneously, and all the water have order are higher in helium and carbon dioxide, several order or magnitude with respect to the air-sea saturated water. The water that we observe here that have a concentration that is lower with respect to the air-sea saturated waters is due to the high salinity of the waters and to the salting out effect. In this plot, we can observe that there is a correlation between the temperature found in the water and the amount of helium and carbon dioxide dissolved. We can observe that the water that are characterized by higher temperature, up to 60 degrees Celsius, are the same water that have the higher concentration of helium and carbon dioxide. We investigated the isotope composition of helium in order to understand, to find the source of these gases in waters. In this plot, we coupled the RA ratios, that is the helium-3 and helium-4 ratios in the sample, normalized to the helium-3 and helium-4 in the air. We found that most of the samples are characterized by a radiogenic dominated isotope composition. On the contrary, we have the water of group 1 that are the only one that have a higher percentage of MORB contribution. In order to calculate this percentage, we used the equation of Sano and Wakita in 1985, and we found that there is a geographical distribution of mantle helium along the Dead Sea Fault. In particular, we have that the waters belonging to the group 1 that were located in the northern part of the Dead Sea Fault are the only one characterized by a range of mantle contribution that change from 18 to 35. On the contrary, in the center and southern part, we have low contribution of mantle helium. In order to investigate the carbon origin, we have compared the carbon dioxide helium-3 ratios with respect to isotope of the carbon. And we used this graph that was proposed by Sun and Martin in 1995, and we assumed it to be as the sedimentary, the limestone, and the mantle as end members. And we can observe that most of the samples are located in the central part, so we have a contribution from all these end members. But the groups of the groups 1 that is located in the northern part have a higher mantle contribution. So what are the implications and the conclusion of this study? We found a geographical distribution of mantle helium and carbon dioxide. In the northern part, where we found the higher mantle helium and mantle carbon dioxide, Sciale et al. Found an anomalous heat flux that reached 70 megawatt of flux. Moreover, a study from Sciale et al. Investigated the dip of the Mo along the Dead Sea Fault. And he found that there is a variation of the depth of the Mo along the Dead Sea Fault. In fact, we have a variation of 10 kilometers between the southern part and the northern part. So we can justify this higher mantle and helium contribution due to the different depth of the Mo in the northern part. That is there is the shallowest Mo in this point. Thank you.
Muchísimas gracias por esta interesante conferencia.